Alrighty, lads and ladies, welcome back to the wonderful wild world of integral calculus. We are closing in on this new calculus operation that we introduced, at least in spirit last time, by talking about trying to find areas bounded by curves. I want to start by addressing a video, problem with the video from last class's meeting. I've gone back and updated this. I didn't realize when I hosted the video that it was set to private. I don't, maybe YouTube changed the default setting or something like that. In the past, I never had to tell YouTube to make the videos public, but in any case, got a few emails saying that the link to the original upload wasn't working. Looked at it myself, it loaded fine. But of course, I'm logged in as me, so it didn't mind. And then when I got a later email saying that the video was marked as private, I was like, oh, so I went to the settings, changed it. It gave me a new URL, so you're gonna need to follow this new link. The old link is probably dedicated to the private version, but now it should be watchable. I am going to recap today a little bit what we did last time. And this cat here seems to want to get involved. So if you see this face creeping in, there she is. I apologize, but I can't quite grab her where she is now. So this is MAC. Oh, there's one other little announcement thing too. Let's get this done. MAC 2311 section 004, which is Calc 1. And the date today is the 23rd, March 2022. Today, we're going to find more areas bounded by curves. Oh, watch out, kid. All right, you know what? No, baby, I love you. I love you. Yes, you know how this goes, baby girl. Here. Say goodbye to the nice people. All right, get the fuck out. I love you. Get the fuck out. Okay. More on areas bounded by curves. We're still in section 5.1, and we might drift a little bit into 5.2, depending on how you guys feel about things. Obviously, on Monday, there were a lot of people taking the makeup test, and because the video was set to private, I know that a lot of us haven't had the chance to review the content from Monday's lecture. So like I said, little recap, I'm gonna go gentle. Announcement-wise, obviously, there's the video link. For the 321 lecture. It's been fixed. The other thing is that if you emailed me asking me to grade your test by today so you could make the decision whether to stay in the class or not, it's done. So exam 2 has been graded. For anyone who requested early grading. Now, there are some folks who expressed some interest or concern, but didn't explicitly ask me to grade their test early. And there was at least one person who talked to me a little bit about grade concerns, but when I went to grade their test early, didn't have the written work. So I just want to say, if you're like, if you think that you asked for the test to be graded early and your test hasn't been graded yet, then I need some communication from you. Either I didn't have what I needed to grade your test, or I didn't receive your request to grade the test early. So if you're in that position where you're like, I really need the test graded by today because today is the withdrawal deadline for the class, but your test has not yet been graded, that means I need some more communication from you. Something is missing or not working. But otherwise, those are all done. So that is a good thing. All right. Last time, we introduced this problem. We asked, how can we find or at least approximate the area bounded by the graph y equals f of x, and the x-axis, or horizontal axis if the variable is something other than x, on some interval, say the closed interval from a to b. For certain functions, this is super easy, right? Like if you have a linear function, then that area is going to be like either a triangle or like a little rectangle with a triangle on top, which we call a trapezoid. But for more general functions like quadratics, cubics, sines, cosines, logs, whatever, the boundary is curvy, which makes using basic geometry formulas to find the area impossible. And what we came up with, or what I described last time, was a mechanism for approximating the area that area being the area bounded by this curve from and the x-axis from a to b, or on the interval ab. So this pencil shaded area, and the convention I use is that I'll shade the exact areas in pencil, so we can kind of compare and contrast. Right. We want to find this area. And the trick is, well, one possible trick is to chop up this interval from a to b into a bunch of little intervals. And then on each of those little intervals, to make a rectangle. And the way I'm drawing it here, the height of this rectangle is determined by the value of the function, the y value up here, at the right end point of this little sub-interval. And you do that for each of these little sub-intervals. And you add up the area of all the little purple rectangles. There was some notation. So each one of these rectangles had width. We call delta x, which is always b minus a over n, where n is the number of rectangles. Each of these x values in here that denote one of the boundaries of the subintervals get a name. A we call x0. This guy we call x1. This guy would be x2. This guy would be x3, x4. And b we would call x5. So here n is equal to 5. 5 rectangles, each of the same width. And then the x sub I, like x0, x1, x2, x3, if you want a formula that tells you how to, where is this x value in relation to a, that is a, so it says like start here, and then to get to the third one, you start at a and walk 1 delta x, 2 delta x, 3 delta x. And in general, you start at a and walk I copies of delta x. So the endpoints of the subintervals are called xi. Kind of morally or logically, what we're doing here is we take the interval a to b, we chop it up into n equal length subintervals. So like here's the first subinterval, here's the second subinterval, here's the third subinterval, fourth and fifth. So here n is 5, and it's always the number of rectangles, aka the number of subintervals. Chop a to b up into n equal length subintervals, and then construct a rectangle on each of those intervals. As I've done it here, where the height of the rectangle is determined by the value of the function at the right endpoint of the subinterval. So the first subinterval here is from a to x1. The right endpoint of that subinterval is x1. So I let the height of this rectangle be determined by the y value of the function at that right endpoint. This gave us the thing we call Rn. And we wrote this in the sigma summation notation, which we reviewed last time. This would be the sum from I equals 1 to n of each one of those heights, which is f of xi, times each one of those widths, which is delta x. And this capital, this symbol here that looks like a big E is the Greek letter sigma. It stands for the word sum, like S-U-M, meaning to add up. So that's just a shorthand for the big addition problem, f of x1 times delta x plus f of x2 times delta x plus blah, 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 all the way out to f of xn times delta x. We discussed that it is possible to construct these rectangles a few other ways. This was with right endpoints. If you let the height of each rectangle be determined by the value of the function at the left endpoint of each subinterval, so if you use left endpoints, then we got the thing we called Ln. Which is very similar. Only instead of the sum running from 1 to n, it runs from 0 to n minus 1. Everything else is the same. So the only thing that would change between using right endpoints and left endpoints is the height. And what this says is that your first height should come from f of x0, aka f of a. Your second height would come from f of x1, and so on. And that sigma notation is just shorthand for f of x0 delta x plus f of x1 delta x out to f of x sub n minus 1 delta x. Rather than taking the time to draw all of the pictures, I'm going to give you two other formula here to approximate the area under a curve. If you were here Monday, we got these then, but I just want to put them all in one place and make sure everybody who wasn't here on Monday, or at least at the start, has the opportunity to look at this and ask questions. If you want to construct, show you some pictures here. Come on. So this is a right endpoint Riemann sum, right? A right endpoint rectangle approximation. Here's a left endpoint rectangle approximation. Yeah, you see left endpoints for the height of each rectangle comes from the height of the curve at the left side. Over here, the height of each rectangle comes from the height of the curve at the right side. So these are the two formulae, right endpoints, left endpoints. The left endpoint picture looks like this. The right endpoint picture looks like this. We talked about ways to improve this, and the kind of brain dead thing is use more rectangle, right? If 3 rectangles is better than 1 and 4 rectangles is better than 3, then a rotten dickload of rectangles is better than fewer than a rotten dickload of rectangles. So by using more and more and more rectangles, the area of all those rectangles gets closer and closer to the actual area under the curve. But that wasn't the only way to improve things. One way to improve things is using midpoints for your height. Oh, Simpson's rule is not what we're looking for. So sample points, midpoint. Here it is. So rather than letting the height of each rectangle come from the value of the function at the left or the value of the function at the right, I can let the height of each rectangle be determined by the value of the function right in the middle. And this is one way to get a slightly better approximation. What this yields is the thing we call M sub n, which would be the sum from I equals, let me use the notation the book uses. They call it xi star, right? And they go 1 to n. So 1 to n of f of xi star delta x, where the xi star is the midpoint between x sub I and x sub I plus 1. Now, what is that? Well, there is a formula for this if you want it. It's going to be 1/2 xi plus 1, where the xi's come from this guy. We can write this out long form also if you want. Of course, this would be f x1 star delta x plus f of x2 star delta x out to f sub f of xn star delta x. And there was one more, the trapezoid rule. Tm, and this is 1/2 of ln plus rn. That's the nice way to calculate it. In reality, moving forwards, we're pretty much just going to use rn. But there are homework problems that ask you to do left endpoint and midpoint approximations. All right. To see the explicit calculations done with Rn and Ln in the examples we worked last time, you'll have to review that video. I can run you as quickly as possible back through the basics. We worked the example here where we wanted to approximate the area bounded by f of x equals x squared from x equals 0 to x equals 1, i.e. on the interval 0, 1, using, I think we did L5 and R5. So the way we do this we'll do the L5 calculation first. L5 is the sum from I equals 0 to 4, right? From 0 to n minus 1, f of xi times delta x, where delta x is b minus a over n. Your first actual calculation step in all of these problems is finding delta x. So a and b are the endpoints of the big interval we're working with. So, this is the interval from a to b. So a is 0, b is 1. So this is 1 minus 0 over n is the number of rectangles we are using. Since they said to use L5 and R5, n is equal to 5. So our delta x is 1/5, which means that the xi's, which are always a plus I times delta x, is just I times 1/5. So x0 is 0, x1 is 1/5, x2 is 2/5, x3 is 3/5, x4 is 4/5, and x5 is 5/5, or 1. The pictures are great for understanding what's going on, but the calculation is a pretty raw thing. I'm just going to plug this shit into this apparatus. I'll write things out gently here. So this is f of x0 times delta x plus f of x1 delta x plus f of x2 delta x plus f of x3 delta x plus f of x4 delta x. x0 is 0, x1 is 1/5, x2 is 2/5, and so on. This is 0, 1/5, 2/5, and so on. And f of x is x squared. So f of 0, I'm going to plug everything in here now. This will be 0 squared times delta x is 1/5 plus f of x1 is f of 1/5, which is 1/5 squared times delta x, which is also 1/5. x2 is 2/5, so f of x2 is 2/5 squared times delta x is 1/5. x3 is 3/5, so this is 3/5 squared times delta x is 1/5.
Where are you getting the squared from?
F of x is x squared. So f of anything is that thing squared. So for example, here I have f of 0. F of 0, if you look here, would be 0 squared. So f of 0 is 0 squared. Or here I would have f of 1/5. The function f of x is x squared. So f of 1/5 is 1/5 squared. So I'm taking these numbers x0, x1, x2, and plugging them into this function, then multiplying by delta x. Does that make sense?
Yes, thank you.
Great. We did the calculation. I think this one came out something like 0.24. Let's just see. So 1/5 squared is 1/25, and then 4/25, and then 9/25, and 16/25. Factor the 1/5 out. One element list. Oh, it thinks I'm trying to do something else. There, yeah, 0.24.
I'm sorry, how come the x sub 5 is not in there? Oh, just because it's 1?
Good question. No, so if we look back at the recipe for Ln, this is what makes Ln and Rn different from each other. Ln has the same thing inside the sum, but that sum runs from 0 to n minus 1. So Ln starts at x0 and ends at the second to last guy, xn minus 1. Rn starts at x1, right, with I equal 1, and ends at xn. So the difference between the two is that Rn runs from 1 to n. So your terms here are like f of x1. It starts with this guy, not this guy, and ends with the last guy. Ln starts with this guy, starts with x sub 0, and ends with not the last guy, but the second to last guy. So in L5, we would sum from 0 to 4. And in R5, we're going to sum from 1 to 5.
Thank you.
Yeah. So this came out to 0.24. And a similar calculation for R5. Sum from 1 to 5. F of xi delta x, which is f of x1 delta x. Sloppy there, plus f of x2 delta x plus x3 delta x 4 5 delta x, which was going to be 1/5 squared times 1/5 plus 2/5 squared times 1/5 plus 3/5 squared times 1/5 4/5 squared times 1/5 plus 1 squared times 1/5. Well, this guy came out to 0.44. So we made the observation that the actual area bounded by this curve from 0 to 1 is probably between 0.24 and 0.44. One of these is likely an overestimate and the other is an underestimate. Sorry, just wondering why I was sweating. I realized my wife left the heat on this morning. So the two pictures that came with this. Sketch something rough and quick here. Here's x squared from 0 to 1. L5 is so this is 1/5, 2/5, 3/5, and 4/5. If we're trying to understand how L5 worked, L5 took his height for the first rectangle from the left endpoint. So the first rectangle, there was actually height 0. The height for the second rectangle came from the function value at 1/5. The height for the third rectangle came from the function value at 2/5. A fourth from the function value at 4/5, sorry, 3/5, and the fifth from the function value at 4/5. So this is the picture for L. And we see that L5 is an underestimate because there's pencil area there that's not being measured in the rectangles, right? The rectangles are missing stuff. The picture for R5. This is a bad picture. Something like this. The height of each rectangle is determined by the function value at the right endpoint. So the exact area I'm after is the area bounded by the curve, which is the pencil shaded area here. And definitely these rectangles overestimated, right? Because we've got all sorts of stuff here. In the rectangles that is outside the pencil shaded area. So L5 underestimates, R5 overestimates. And for any increasing function, that will be the case, right? If your function is always increasing, then it's smaller at the left side than it is at the right side. So if you take your height coming from the left side, there will always be bits of that area on the subinterval that that rectangle misses, right? Look at this subinterval. This rectangle misses all of this area here because the height of the rectangle is coming from the value of the function at the left endpoint, and it is an increasing function. Similarly, R5 will always overestimate for an increasing function. Same logic, just turned around. You should be asking yourself, what about decreasing functions? Or what about functions that do a mixture of increasing and decreasing? And the answer there is that decreasing functions, you turn things around. R5 will underestimate and L5 will overestimate. For functions that do a combination of increasing and decreasing, there's no easy way to say. The big question is, how do I go from these approximate areas to the exact area? I can be confident that the exact area here is somewhere between 0.24 and 0.44, because I know that this purple is too big and I know that this purple is too small. The ideas like use midpoints, use the trapezoid rule are valid, and those are good ways of improving your approximation, but they will never get you the exact answer. What we need is mo rectangle, like a lot mo rectangle. Get the exact area, and this is where we wrapped up last time. You can take your Rn and find a nice formula for it, and then send n to infinity. Or you could do this with ln or any of the other guys. We'll call those schemes. But you need to use infinitely many rectangles. That's how you get the exact area. No finite number of rectangles is guaranteed to give you the exact area. Certain special cases, maybe. But if you want to guarantee that you get the exact area, what you need to do is stack in more and more and more rectangles. The big challenge in using infinitely many rectangles is that my lifespan is finite. I cannot do the calculation for infinitely many rectangles by hand, right? Like if I had infinitely many rectangles, that would mean that this addition problem right here would go on and on and on and on and on forever. And I will die before I finish writing it down. Other challenges, of course, delta x has an n downstairs. So as n goes to infinity, delta x goes to 0. So each one of these would be multiplied by 0. It's a problem, right? It's a problem. And it's a problem you're going to tackle in Calc 2. When we talk about infinite series, you'll learn all the rules for handling infinite addition problems there. For our purposes, it's sufficient to say that we're going to find a formula for Rn that depends on n. So like rather than starting by saying use 5 rectangles and then doing the calculation, I'm going to assume I'm working with n rectangles. I'm going to use some special summation formulae that I introduced last time, and I'll recap those for you, to evaluate the Riemann sum, Rn, in general for n rectangles. And then I'll take a limit as n goes to infinity. So a quick reminder, these things are called Riemann sums. It's a term you're going to hear thrown around a lot. Just be ready for it. The formulas for adding up the areas of rectangles, anything like that is called a Riemann sum. So right endpoint, left endpoint, midpoint, trapezoid, they're all Riemann sums. And I have some special summation formulas for you. If you add up a constant from 1 to n, this is c plus c plus c, blah, 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 plus c n times, you're going to get c times n. There's a fun story behind this one. If you add up the first n integers, so 1 plus 2 plus 3 plus blah, 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 out to n, this always comes out to n over 2 times n plus 1. And most people write it as n times n plus 1 over 2. A very young person proved this. Baby Gauss, little Gauss, when he was in like 2nd grade, proved that shit. If you add up the first n squares, 1 squared plus 2 squared plus 3 squared, all the way up to n squared, this gives you n times n plus 1 times 2n plus 1 all over 6. And there's one more of these. If you want to see them discussed at length, again, it's in the video from Monday. There's one more of these that we're going to need from time to time, and that's the sum of the first n cubes. So it'd be 1 cubed plus 2 cubed plus 3 cubed all the way out to n cubed. This turns out to be the square of the second one. And a really fun project is proving that. All right, prove that this thing is equal to this thing squared. So we arrive at the point that I promised we would do last time, and that is finding the exact area under the parabola x squared from 0 to 1. we know that that answer should live between 0.24 and 0.44 from our approximate calculations. And we know that to get the exact area, what we need to do is find the limit as n goes to infinity of Rn. Like I said, you could use Ln or Mn or Tn, but all of those are more cumbersome to work with than Rn. So we will always send n to infinity in Rn. It's just the easiest thing to do. You get the same thing with the other ones. You just have a bigger headache. And that means we need a formula for Rn, where n is left as a variable. It's easy enough for me to say, approximate this area using 5 rectangles, or approximate this area using 10 rectangles. It's much harder to say, find me a formula that you would get for approximating this area using n rectangles. Right? If I give you a specific number for n, then you just plug everything in. It's a finite sum, you can write it out and give me the number. If I don't give you a specific number for n, then you need to leave n as a variable and find a nice formula for it. And that's considerably trickier. Now remember what I said, your first step, any Riemann sum problem, calculate delta x. Delta x is always the length of the interval divided by n, the number of rectangles. Here, n will be left as a variable. A and b, though, those are concrete numbers. They are 0 and 1. So this is 1 minus 0 over n, which is 1 over n. The other thing we need, I got to know those xi's. I need to know the endpoints of my subintervals. And that always follows from the rule xi equals a plus I times delta x. A is 0, I is I, delta x is 1 over n. So this is just I times 1 over n. Now, Rn, I know, is the sum from I equals 1 to n, again, leaving n as a variable, f of xi times delta x. Which is the sum from I equals 1 to n. The xi's here are I times 1 over n. So this is f of I times 1 over n. And delta x we know is 1 over n. Remember, as in the previous example, f of x here is x squared. So f of I times 1 over n, I still have my sum, I from 1 to n. This piece, f of I times 1 over n, is I times 1 over n squared, because f of anything is that thing squared. F of dog shit is dog shit squared. F of your mom is your mom squared. F of I times 1 over n is I times 1 over n squared. And the 1 over n from delta x still just chilling. The name of the game is to get a formula for this that doesn't have this thing. Now, of course, I cannot just ignore this thing. This thing is the most important part of this formula. It says you're adding up all this stuff as I goes from 1 to n. But if I simplify the stuff in here and use the rules for capital sigma discussed last time, I can apply one of my summation formulas. So I'm going to walk you through this. Still sigma I from 1 to n. I times 1 over n all squared is I squared times 1 over n squared. And then I still have my 1 over n here. The sum is being done as I goes from 1 to n. So this is like 1 squared times 1 over n squared times 1 over n plus 2 squared times 1 over n squared times 1 over n. And this is sigma I from 1 to n, I squared times 1 over n cubed. And I claim that this 1 over n cubed can come out of the sum. To see why, the following is optional. You don't need to write it, and it would not be a unnecessary part of this. But let me just write out what this sum is to justify the next step for those who are curious. This would be 1 squared times 1 over n cubed plus 2 squared times 1 over n cubed plus 3 squared times 1 over n cubed plus all the way out to n squared times 1 over n cubed. Right, this piece, the 1 over n cubed piece, doesn't change with I. It's the same in all of these terms. So I can factor 1 over n cubed out. And what's left is 1 squared plus 2 squared plus 3 squared out to n squared. So what is that? That's 1 over n cubed times sigma I from 1 to n of I squared. So the red is optional. What's not optional is realizing that this piece can come outside the sum here. The rule? Something can pass in and out of a sum like this if it doesn't have any i's in it. Right? This down here says that the sum is indexed by the parameter I. In other words, the symbol I is the thing that's considered non-constant for the sum. So if you've got i's in you, you got to stay inside. If you don't have i's in you, you can pop in or out as you choose. Just like with derivatives, how constants pop out of derivatives, constants pop out of sums. The way we described this on Monday was saying that it's a linear operator. Now this should look familiar. This is one of the things that we just had a formula for. One of our special summation formulas, or you can see it from here as well, that the sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. So this is 1 over n cubed times n plus 1 to n plus 1 over 6. I'm replacing the sum by this, which is the formula for that sum. So the exact area is going to be what I get by taking the limit as n goes to infinity in Rn. Right, it's the infinite rectangle approximation. Infinitely many rectangles means we're going to get the exact area. And then the formula for Rn is this. 1 over n cubed times n plus 1 to n plus 1 over 6. All the hard work is in manipulating the sum, right? Getting to this point, that's most of the work. The only other step that requires a little bit of love is taking this limit. It's been a while since we did limits at infinity, right? We did that way back in section 2.6. We touched on it a little bit with L'Hopital's rule. Here it is again. I'll just do a bit of algebra here. I'll distribute this n, and that gives me n squared plus n times 2n plus 1. And I'll multiply the two fractions together, so I have 6n cubed downstairs. Then I can FOIL out the top. Oh, sorry, my wife just texted me. She got a 92 on her physics test. Sorry. All right. So we can then FOIL out the top. And finally, if I want to take this limit, I think the easiest way here, if you divide top and bottom by the fastest growing term, which is n cubed, you get 2 over 6 plus 1 over 6n plus 2 over 6n plus 1 over 6n squared. All right, really, I'm just splitting up the fraction, right? This over the bottom plus this over the bottom plus this over the bottom. I can get away with this because the bottom only has one term. More generally, you remember back when we talked about these limits in 2.6, we would divide top and bottom by the fastest growing term. That's the same thing. All of these, 1 over 6n, 2 over 6n, 1 over 6n squared, go to 0. So this is 2/6 or 1/3. That is the exact area bounded by x squared from 0 to 1. It's a lot of work. It's a lot of work. But it's possible. And this is fucking mind-blowing if you live in the 13th century. If you live in the 14th or 15th century, you might start believing that there are humans alive who can calculate things like these. But prior to Newton, this was not doable. And prior to Riemann, we're talking like 19th century now, 1850s. Prior to Riemann, nobody had a nice way of describing what they were doing. It was like you hand the problem to a mathematician, they do some black magic, and you get an answer. Riemann was the first to really structure the argument in a way that makes it followable and clean. And most importantly, Riemann gives us a nice way to prove something called the fundamental theorem of calculus, which is going to allow us to do this much faster. So just like when you first started learning how to take derivatives, I made you work with the limit definition of the derivative, the whole lim h to 0 thing, and it was a pain in the ass. And then you got some differentiation rules and you were like, never again. We're in that part here, right? Where we're doing this kind of from the limit definition. And later, once we prove the fundamental theorem of calculus, I'll have better tools for you. But just like with the differentiation rules, you need to understand how the shit works. So we need to practice this. We need to practice this more. And we also need to learn to interpret results. So this is the only example I'm going to do like this today. So I want to take a minute here and see if there's any step of this process that you guys would like to look at more carefully, because God knows it's quite a bit. Is there anything from this first bit of the exercise that we want to look at more closely? Anything where you're like, ooh, how'd you go from there to there? Or why did we do this?
Are we ever going to have to deal with something that's like, you know how it says like x squared up at the top?
Mhm.
If it's going to be like longer than that, will we just like plug it in like how we did this?
Yep, that would change this step to this step, right? This step to this step is where I plugged into the function f to get I times 1 over n all squared. If that was x squared plus 1, this would be I times 1 over n squared plus 1. If it was x cubed, it would be I times 1 over n all cubed. We'll do this for lots of different functions. And there are problems where I give you a sum like this, and I ask you, what's the function? There are problems where I give you the function in the interval, and I ask you just for this sum without evaluating it. So there will be plenty of more complicated problems like that. And going back and forth and recognizing where this piece comes from is going to be a big part of those problems.
Okay, thank
Let me push this up a little bit. Questions from here to here? Questions on the last few steps? Okay. The other thing I promised to talk about today is an application. Fitting that we got news about my wife's physics test. Not that that should matter to you guys, but physics is one of the places where applications of calculus in general, but integral calculus especially is a big deal, and the interpretation can be a little bit tricky. So suppose I want to find and physically interpret the area under a velocity function v of t from some time t equals a to some later time t equals b. This doesn't have to be a velocity function. You can do this with acceleration as well, but I think velocity is the place where we're going to most quickly realize what's going on. Let me sketch for you just an arbitrary velocity function. And for this example, I'm going to make the function positive. There's some subtlety here when v is negative. But let's say this thing just looks like this. And I'm starting here at A, and then over here at B. So the area would be this area. Shading areas. Okay, there we go. All right. close enough for jazz. Okay. I'm going to draw in just one rectangle. We'll call this xi, and we'll call this xi plus 1. And I'll go ahead and assume that I'm using a right endpoint Riemann sum. Okay, we have the understanding here that there are many rectangles that I could draw on if I wanted to. I'm just drawing one as a kind of representative class, right? So yeah, imagine there's a bunch of other rectangles in here, but I just want to focus on one. The width of this rectangle is delta x, or I'm sorry, delta t, these should be t's. So we're using the variable t here. Delta t, which is a length of time. Right, this is a velocity function. The inputs are t's, the outputs are v's or velocities. The height would be v of t sub I plus 1, which is a velocity, which is a distance divided by a time, right? Velocities are distances over time, or displacement over time, if you're being very picky. But for now, let's just think distance. So the area of that purple rectangle is the height times the width, which is a velocity times the time, and velocities are a distance over a time. So if you multiply something that measures distance over time by something that measures time, what you get out is a distance. This is a big, big deal. This is how the odometer in modern cars work. This is how your drone, when you fly it around, knows where it is. It's using accelerometers to track the acceleration. It calculates the velocity from that, and then uses the velocity to calculate the distance traveled, exactly like I'm showing you here. It's called a PID loop. It's a big deal in control systems if you ever get into that stuff. My industrial engineers will learn all about that eventually. The thing I want you to take away from this little moment we've had is that the area under a velocity curve is going to be a distance. Now, again, I'm assuming that the velocity function is always positive. And the sticking point there is that if the velocity is negative, you're going backwards. If the velocity is positive, you're going forwards. So in general, when you calculate the area bounded by a velocity function, you're going to get a displacement, which is a change in position. And that's not always the same as distance. I'm going to tackle that in detail on Friday. But I'd like to play a little game here where we're going to try and approximate a distance traveled. Let's do it. Let's say a ball is rolling along a track with velocity v of t equals 1 plus 2t. Find the distance traveled from time t equals 1 to t equals 3. Velocity here is in meters per second, and time is in seconds. Keep everything in SI units. The important thing is that you recognize what you're trying to do is find the area under this curve. So to go from velocity to distance traveled means finding the area bounded by this curve. You might be thinking, oh shit, here comes a big nasty Riemann sum. But because this is a linear function, the region isn't curvy. Because the graph of this thing is a straight line, y-intercept 1, slope 2. What we're looking for is not so hard to find. Looking for this area. This area equal to the distance. And because the boundary isn't curvy, I mean, sure, you can set up a Riemann sum here. You could send n to infinity in Rn, but you're giving yourself a nasty headache when one isn't necessary, because I can think of this as a little rectangle with a triangle on top. And my lazy ass is definitely going to do that. Let me call this A1 and call this A2. And observe that the total area there, which is the total distance, is the little rectangular area plus the little triangular area. I need the height and the width of the rectangle. I need the height and the base of the triangle. So I need these 2 points. I need the y values of these 2 points. To get that, you plug the t values in here. So when t is equal to 1, we have 1 plus 2 times 1. So this is the point 1, comma 3. When t is equal to 3, this is 1 plus 2 times 3. So that's 1 plus 6, which is 7. So this is 3, comma 7. So the area of the rectangle is this, which is 2, times this height, which is 3. Plus the area of this triangle, which is 1/2 base, which is 2, times the height, which is 7 minus 3. 7 minus 3 is 4. Just using the fact that this is a rectangle, and the fact that this is a triangle, and the well-known formulas for the areas of rectangles and the areas of triangles. So that's 6 plus 4, which is 10 meters. So next time we're going to look at a few more areas beneath curve problems. I'll do one more calculation where we take a limit of a Riemann sum. And then we're going to look at some of these velocity problems where the velocity function isn't necessarily a straight line and isn't necessarily always positive. Those are two ways that these problems can become a little bit more complicated. If the velocity is curvy rather than being a straight line, then we're going to need to do the limit as n goes to infinity of Rn type thing if we want the exact answer. And if the velocity function is sometimes positive and sometimes negative, then we need to count the area beneath the horizontal axis as negative and count the area above the horizontal axis as positive. And I'll talk to you about how to interpret those things in terms of the physical situation. But here we would say that the distance traveled is 10 meters. So the ball is 10 meters from time t equals 1 second to time t equals 3 seconds. And that's it. So that's the area bounded by the velocity curve. Okay, I'm gonna go ahead and let you guys go here. Take a look at the homework. So make sure I get your homework set posted the other day. No. Okay, so I'm going to go ahead and post your fresh homework set. It's going to have some problems where you're calculating distances like this, calculating areas under curves, both exactly using the limit as n goes to infinity of Rn and approximately using some finite number of rectangles. Work on as many of those as you can between today and Friday. And then on Friday, we're going to try to tie the whole picture together. We're going to see curvy velocities. We're going to do some more practice with both exact and approximate areas. And then that will set us up nicely for Monday when we can introduce the fundamental theorem of calculus and sort of start approaching these from a nicer perspective. So 5.1 is nasty, right? Riemann sums, nobody likes working with Riemann sums, including me. They're a little bit nasty. But you need to be comfortable working with them in order to understand the object we're going to define on Monday, which is the definite integral. And we're going to need a solid understanding of Riemann sums when we go to prove the fundamental theorem of calculus, which is the tool that's going to let us stop doing the Riemann sum stuff. So that's it from me. If you guys need anything from me, reach out the normal ways. And exams, the remainder of the exams, people who didn't ask to get them graded early, will be ready by Friday if you took it last Friday, or next Monday if you took it this Monday. Okay. Alrighty, I'm gonna go ahead and end the meeting here. Take care of yourselves, guys, and I'll see you on Friday. Did I see something? Okay.